Example 18, accelerating blocks. Block 1, mass 8 kilograms, is moving on a frictionless 30-degree plane. This block is connected to block 2, mass 22 kilograms, by a massless cord that passes over a massless and frictionless pulley. See figure on left. Find the acceleration of each block and the tension in the cord. All right, so now we have a chance to try out that reasoning strategy. So it says to first identify the objects of interest. So in previous examples, we've just had one object of interest, like a sled and its rider. But here, we have two different masses that both seem pretty interesting. So I think we're going to look at the forces acting on each of them. And that's going to be our next step as we're trying to move towards that free body diagram, is I'm first on this picture going to figure out the forces that are acting on mass 1 as well as on mass 2. So we can start with mass 2. What are the forces acting on mass 2? And I'd encourage you, if you have an idea at this point, go ahead and pause the video, write down any of the forces, draw them on the picture for mass 1 and mass 2, and then you can compare notes in just a moment. All right, well, let's see. One of the forces that's going to be always acting on them is the weight, or that of the force of gravity, right? And what direction is the weight force? It's going to be always down. Straight down, no less. And to keep it clear, because it depends on different mass than M1, I'm going to write the weight force as M2G. All right, what other forces are acting on mass 2? There's another one, right? And it comes from the fact that it's connected to this massless cord, right? Anytime you're connected to a cord, that's going to produce some tension. In what direction? Remember, it's always pulling on whatever object it's connected to. So we're going to have a tension that is pulling in the upward direction. So I'll label that with a T, and I promise I will stop sharing the slides soon, but I want to get some things down before we switch to that. All right. And notice this hanging block isn't in contact with anything else. It's not touching the side of the support, so that's just how it's going to be. It just has these two forces acting. What about M1? Well, let's see. First off, does M1 have gravity or a weight force? Yes, because it's on Earth as well. What's its direction, though? It's going to be straight down. Not down along the ramp, but just vertically down. So the weight of object 1 is M1 times G. All right. Now, does mass 1 have a tension force? Yes, because it's connected to the cord as well. But this tension force isn't going to be acting purely vertically. What direction will it be acting? It's going to be pulling on it up along the slope. Cool. So we have those two forces that are the same. Anything else? Any other forces? Well, notice mass 1 is sliding on the surface. That means it's in contact with the surface. And so anytime you have contact between the surface, you have to check for friction and the normal force. In this case, is there friction? Let's look back at sentence 1. It says moving on a frictionless plane. Aha, so we don't have to worry about friction here. Is there a normal force though? Yes. That one is basically always there if you're in contact with an object and if you have a force pushing into the surface at all. Since we do have a force pushing down, then we are going to have the normal force pushing back. And in what direction will the normal force be? You have to be careful here because it can be tempting to say, oh, it's going to be opposite gravity. It's going to be straight up. But the normal force is always normal or perpendicular to the surface. The normal force instead is going to be at a right angle to the tension and not in the same direction as the force of gravity. I'll try and emphasize that a little more in this picture. There we go. All right. So that's all the forces that I can think of. That's looking pretty good. Something else I really like to add to my pictures before I move on to the free body diagram is I like to label the overall acceleration of the system. In other words, how do I expect these blocks to move when they are released? Or how do I expect them that they're moving in general if they're already moving? Well, to look at that, we can say, okay, M2 is hanging, so it's going to automatically have more pull. How do the masses compare, right? So it says mass 1 is 8 kilograms, 8.00 kilograms to be precise, and mass 2, meanwhile, is 22.0 kilograms. That means mass 2 is much bigger. So if it's a tug-of-war between the two blocks, which one's going to win? This mass 2 is definitely going to win. So the whole system is going to be accelerating towards mass 2 falling. So I'll fill that in there. And I think at this point we've gotten most of the things from the problem statement, except one extra detail that I do want to mention is this frictionless 30-degree plane. What does the 30 degree tell us? That's telling us about the ramp that this is set at, right? That it is offset up to 30 degrees. Great. So this is our first step, is getting a really accurate picture and being able to label all of the forces acting on the picture, as well as label the overall acceleration. That's what's shown in the figure here. This is sort of already an answer key, which is why it's not given to you, or generally isn't given to you when you're solving a problem. Okay, now what are we solving for ultimately? We want to find the acceleration and the tension. So I'll just jot that down over here. Looking for acceleration and tension. Great. So now I can stop the share so that this gets a little bit bigger, a little easier to read. So we've now identified the objects of interest, identified all the forces acting on them. We are now at a position we can move to our free body diagrams. So let's work on that for each of them. Let's see, I'll do mass 2 over here because it's right next to it anyways. So free body diagram, FBD, mass 2. So I'm going to reduce mass 2 down to a single point, and then I'm going to copy over these forces in the exact orientation. So the tension is coming up, and the weight force is going down. You can write that as W2 or as M2, mass 2 times gravity, whichever you prefer. All right, the other thing I'm going to add, and it's not a force, so you have to be really careful here, is I'm going to add in the acceleration. And I'm just going to put it on the side. That this, I remember, I already decided is falling down. So that's the direction of its acceleration for block 2. Now we're looking really good here, but remember we need to add in the X and Y coordinates. So since this one, I already have 2 forces in the vertical direction, I'm going to stick with the standard X and Y coordinate system. So positive X to the right, positive Y going up. All right, so there's my free body diagram for mass 2. We're looking good so far. Let's do the same thing for mass 1. All right, we're going to reduce mass 1 down to a single point. There we go. And now I'm going to copy down the forces acting on it as shown. So the tension is going up along the slope, normal force sticking out perpendicularly from it, and the weight is coming down, W1. Now with this one, if I stuck with the traditional horizontal and vertical axes, it would line up with none of my forces, not one of them. Actually, it would line up with the weight, but I'd have to break down the normal force and the tension, and that's a pain. It turns out there's a simpler way to do that, and that's to rotate our coordinate axes, right? So I could rotate this and say that the tension is pulling in the positive x direction. And since this is at a right angle, the normal force, I can say the normal force is acting in the positive y direction. And that's going to make our math a lot simpler. Now, one key detail is we have to figure out how far off this weight is from the y-axis here, right? In other words, how far have we rotated it from being just straight down? Because normally, the weight would point in the y-axis. So how much is it shifted away from the y-axis? Well, this is just going to be how much we have rotated our inclined plane up. This is going to be 30 degrees that we have offset W1 from its default of being in the negative y direction. Alrighty, so this is our free body diagram. I have seen students, if you really don't like rotating your reference frame, the other way you can approach it, it doesn't seem to be as successful, but it does work, is you can just rotate your forces in your perspective and say the normal force is up, the tension is to the right, and now the weight is sticking off at this kind of funny angle. Right, that's the 30 degrees. And so we have our standard positive x and positive y directions. So that's basically the same as this. It's just rotating your head so that it looks like it's flat. It looks like it's not rotated. So if this makes more sense to you, you're welcome to use it as long as you make sure to properly rotate the weight. This is a little confusing to me, so I like to stick with what matches my picture. Now, the last thing I need to add in is my acceleration. We have our x and y axis very nicely in there. Acceleration is that the block is accelerating in the direction that the rope is pulling it. So that is the direction of the tension. Again, this is not a force, so I'm not drawing it connected to any of the forces, but in my picture, it would be going in the same direction as that tension. Alrighty, so this has been quite a bit of work, but the good news is we are now in really good shape to solve the problems, believe it or not. So we can note our equations, right? And what are our key equations for this chapter? Well, we're looking at, once again, Newton's second law. The sum of the forces, or the net force in the x and the y direction, is equal to the mass times the acceleration in the x or the y direction. So let's go ahead and start with M1 because we can. So net force in the x direction is equal to mass times acceleration in the x direction. Looks like we'll just fit in here. So we're looking at M1. How many forces are going in this x direction? Well, it turns out there's just one, the tension. Now, is that in the positive or the negative x direction? Well, it's going right towards the positive, so great. We can fill in a positive tension. That's going to be equal to, on the right side, so the left side, we've just done the net force. We've summed up all of the forces we have. On the right side, we need to substitute in the mass that we are focusing on in our free body diagram, as well as the acceleration, which can be the letter A with a positive or a negative sign, depending on the direction. So this is M1, so I'm going to fill in an M1 here. And then it is multiplied by A, which is in the positive direction. So I can just put in a positive A. So great, we get that the tension is equal to M1 times A, right? Where A is positive, so that whole expression stays positive. Very good. All right, now that's our x direction. What about the y direction? Let's check that too. So if we sum up the forces in the y direction, I'll switch colors so this is a little more distinctive. And I'm going to first write out my equation because that's really good practice. It helps you get partial credit on assignments. So what forces do I have acting in my y direction? Well, I have the normal force, and oh, actually, notice I have this weight force, and it's acting in the y direction as well as the x direction. Oh, this is a more complicated problem than I thought, right? So before I can get to this, I need to add in the x component of the weight. And this is something new, right? We haven't done a whole lot of it, having to deal with the x component of weight. So positive tension still, but minus W1x. So for that, we're going to have to come back here and note that this forms a triangle with this 30 degrees. And so we have a W1y that we could break down, and I could also draw in a W1x. To find W1x, I'm going to use this 30 degrees and get W1x, I'm going to have to use sine, which is a little funny. It's because the angle is defined relative to the vertical axis. But there we have it, and y is now going to be W1 cosine of 30 degrees. All right, so my equations aren't quite as simple as I thought, but that's okay. We'll still get through it. So coming back over here, I have tension minus W1x, so minus W1 times sine of 30 degrees is equal to M1 times A. Great. So now that I took that extra step to break it down into x and y components, because I forgot to do that earlier, now we can look at the sum of the forces in the y direction. Alrighty. So now it's much more apparent, since I've broken this into x and y components, that I have a normal force and a y component of the weight. So those are some of my forces that will go into this net force. It is normal force and W1y, and then we have to put in the sign if they're in the positive or negative direction. So the normal force is in the positive direction, but the weight is in the negative direction. It's pulling down towards the center of the earth. All right, this is equal to, once again, we are looking at mass 1 times the acceleration. And this is where, based on previous chapters, it's like, oh, a sub y, we've seen that before. That's our negative 9.8 meters per second squared, right? Not quite, because that was true when we had objects flying through the air. This is no longer flying through the air. We want to know how much its rate, its velocity is changing into or out of the ramp. And it turns out if it's sitting on the ramp, it's not accelerating. It's not falling into the ramp. It's not bouncing off the ramp. In other words, in this picture, our acceleration is purely in the x direction. We don't even have motion in the y direction, up or down. So this acceleration is 0. Let's angle down so we can see a little more. That means the whole expression on the right is 0. I can add the weight to the other side, and we get that the normal force is equal to W1y, which is W1 times cosine of 30 degrees. In this particular problem, this isn't the most helpful result because we don't actually need the normal force to solve this problem. But in any problem that does involve friction, this is a very important result. So you will definitely care about the y direction anytime you have a problem that does have friction. So you want to pay attention to that. Alrighty. So if we're trying to solve for the tension and the acceleration, we look back at our first equation. It has tension, it has acceleration, but that's two unknowns, right? We know W1, because that's the mass 1 times g. But we have two unknowns with one equation. What do we need? We need another equation in order to sort through those two unknowns. How can we do that? To do that, we're going to go back to mass 2. So I'll briefly angle this back up so we can see this again. And for mass 2, We'll once again follow the same equation. What direction are we going to look at? Which one do we care about? Well, here we care about the y direction. So I'll look at the sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. All right, so what forces do we have in the y direction? We have tension and W2. Great. Tension, W2. And are those in the positive or negative y direction? Well, notice tension is going up, so that's positive, versus W2 is down, so that is negative. Awesome. So that is our net force in terms of summing up the forces on the left. On the right, we're going to put in that this is mass 2, because that's the mass that we are focused on here. And then we need to put in the acceleration. So we look back at our picture, and we can note up here that we have acceleration A, because we can work in terms of the same general acceleration A. It's going to be the same acceleration for both blocks because they're connected by this cord. But the key detail here is, what is the direction of this acceleration? Is it in the positive y direction or the negative y direction? This acceleration is in the same direction as W2. It's in the negative y direction. That means when we come over here, we're going to have to substitute in a negative A. That's a detail that's so easy to miss. I see students miss it all the time with these problems. And so we get that we have tension minus W2 is equal to minus M2A. All right. So the good news is at this point, we now have an equation where we know W2, it's mass 2 times G, or 9.8. We know mass 2, and we just don't know tension and acceleration, but those are the same two unknowns we had over here, tension and acceleration. So we've done all of the important conceptual work at this point. Now it's just going to be a little bit of algebra to get this all together. So I'm going to get a separate whiteboard for this. Let's start by writing. Well, let's see first. Before we get on the second whiteboard, how are we going to combine these equations? Well, the way I like to think about it is if you solve both for tension, the tension is going to be the same because it's the same massless cord. So we have the same tension throughout. And so we can just say tension is equal to tension, and that will work out great. So over here, I'll continue this one line further and say that this is going to be tension is equal to weight 2 minus M2A. And up here, it is tension is equal to W1 sine of 30 degrees plus M1A. So this is a lot to keep straight, right? A lot of different variables there. But we are going to start out our new board with tension is equal to tension. What I'm going to do is just use a tension from either of the two equations. So on the left side, we had W2 minus M2A. And that's equal to, on the right side, we had W1 sine of 30 plus M1A. And now we're going to practice working symbolically, practice working in terms of the symbols as opposed to the numbers. But if you prefer, you can at this point plug in numbers for W2, for M2, for W1, for M1. The reason I don't is it's often easier to make rounding errors or just mathematical mistakes and to lose sight of what is what. So the more you can practice working in the symbolic notation, the easier your life is going to get. But I get that it's hard to get there. All right, so I need to now solve for A, right? That's what I'm going to focus on. But notice I have two A's here. So what do? Well, I need to get them to the same side. So to keep everything positive, I'm going to add this m2a to the right side, and I'm going to subtract the w1 sine of 30 to the left side. So let's rewrite this. W2 minus W1 sine of 30 degrees is equal to M1A plus M2A. All right, that helped us out a lot because on the right side, we now only have things that are in terms of A. Since they're both in terms of A, we can factor out that A. So on the right, we can write this as A times M1 plus M2. That's a really nifty trick. On the left side, I'm going to now write this in terms of the masses. So M2G for weight 2, and then M1G for weight 1 times sine of 30 degrees. And now we are almost home, believe it or not. So we're going to divide both sides by this total mass, M1 plus M2. M1 plus M2. So the masses will cancel, and all that we're left with is A here. And we can now plug in numbers, and it's going to be just some plugging and chugging away. So A is equal to, let's see, M2 we said was 22 kilograms. Nice that we have it written out, so we don't need to be scrambling for that, times G, which is our 9.80 meters per second squared, minus M1 was only 8 kilograms. I'm going to drop the significant figures, but we know that we have them, times G, 9.8 meters per second squared, and then times as well this sine of 30 degrees. So that is all on the top, and then divided by the total mass, which is our 8 kilograms plus our 22 kilograms. All right, let's angle this down. Sorry, that got a little low. So when you multiply all this out and divide it out, you actually end up with a pretty simple result. It comes out to a simple, relatively simple 5.88. What would the units on this be? It's going to be meters per second squared. And that is the same acceleration for each of the blocks because the two blocks are accelerating together. What about the tension? We still need to find the tension. Well, if we remember, we have an equation for tension. We have two equations for tension at this point, because now that we know the acceleration, we can plug the acceleration into either of these equations. The one on the left doesn't have a sign, so might as well do that one, but you can do the one on the right just as easily. So let's see if we can fit this on here. So tension is equal to weight 2, M2G minus M2A. And what we're left with, if we factor out the M2, we could do that. M2 is 22 kilograms times G, 9.8 meters per second squared, minus my A, 5.88 meters per second squared, where I've just distributed out the M2. So it's M2 times G minus A. And that is now something we can calculate, right? So if you do calculate that, you should get 86.2. And what would the units on that be? Since it's a force, remember the units are newtons. All right, so this was non-trivial algebra at the end, right? Some definite work to get to that end result. But the real key to this problem, and to all of these problems, is the earlier steps, is the taking a look at how to draw the forces in every direction and how to translate that into a free body diagram. Because once you have a good free body diagram, then you're just plugging and chugging into Newton's second law, the sum of the forces in the x direction and the y direction for all of the objects of interest. And then you can just see where it takes you, and you will get there. If you have questions on this, please do ask. I would love to talk further. I know this is a pretty involved example, but I wanted to give you a more challenging one so that you could see some of the more advanced problem solving before you try out some of the more advanced problem solving yourself. All right, take care, y'all. This brings us through chapter 4.